And we will move on to our next German speaker, Dominique Unruh. And he will tell us something about quantum position verification in the plane in 2D.
Okay, we convinced the computers. So I'm going to talk about quantum position verification in the plane, where plane does not mean airplane, but flat surface. So it's not something to try on the way back. So let me explain what position verification means, and then I come to all the quantum parts. So position verification considers the following scenario. You have a device, a mobile device, or well, something where you can't be sure where it is. And this device wants to prove to some other entities, the verifiers, that it is at a certain location where it claims to be. So this is not like GPS, where the device wants to find out where it is, but where the device knows where it is, but it wants to prove it to others. And then we have some devices for some verifying devices that are somewhere around the area where the prover is. And the basic idea is that those devices send some messages to the prover, and the prover answers right away. And then you can compute that if the answers arrive at the verifiers at a certain moment in time, then due to the fact that the speed of light is limited, the answer cannot have been sent from a place too far from the verifiers, and then you compute that this is the only position where the prover could actually be and answer the questions of all the verifiers in time. So let's look at this problem of position verification first in a classical world to see why we need quantum here. And also this will get us used to the concept of space-time diagrams. So here's a very simple one. Space is one-dimensional. We have a prover and two verifiers, and the prover wants to show that it's here. And up here goes the time. So as the first step in a generic protocol, the verifiers would send 2-bit strings x and y. And they go up here because while the signal travels, time continues, so they reach the prover at this point in space-time. So the prover gets x and y at this point, and now the prover computes a certain function of x and y and sends the answers back to the verifiers, and it reaches the verifiers here. And the intuitive idea is that if the prover would be anywhere else, for example here, then it could answer at this point to this verifier, but it wouldn't be able to answer this verifier because g of xy depends on y, and the prover, which is here, would get y at this point, send the answer, and would be too late. So that's the intuition behind a position verification protocol. But now, unfortunately, we have a generic attack on protocols of that form, because imagine now the generic attack scenario. There is no prover in the place where it claims to be, but the prover, the malicious prover now, has two adversarial devices. One of them is located here and the other here. So they are not where the prover is supposed to be, but the prover will still be able to answer the questions thrown at it. Why? Well, since the prover has a device here and here, it can intercept the signals x and y at these positions, and it forwards them to the other prover, which reaches the other prover at this moment. It also keeps those values, makes a copy of that value, and then at this point in time, the first part of the prover has both values, can produce the answer. Here, the other part of the prover has both values, can compute the answer, and the verifiers get their answers in time. And this approach, this attack works generically. It works in in one dimension like described here. You can also show that in 3 dimensions you don't get around it. It doesn't depend how many verifiers you have. So position verification just does not work. However, this generic attack assumed that we are sending classical messages. Because if you look at this diagram here, it gets, for example, this part of the prover got the value x, sent it on, and kept it, meaning it has to make a copy. And due to the no cloning we cannot do this particular attack. That does, of course, not mean that no attack is possible. It just means this very trivial attack is ruled out. And indeed, in 2011, Burman, Shadran, Fair, Gels, Goyal, Ostrovsky, and Schaffner showed that there is also a generic attack in the quantum setting. It has a message flow that looks also like this here in the classical setting, but it can't just copy the state. It does something complicated called instantaneous, what was the name? Instantaneous local computation, non-local, well, it does something fancy. And breaks also any protocol. However, the generic attack uses exponential and an exponential amount of entanglement, so it does not rule out that there are some attacks that work either by putting a limitation on the computational power or on the amount of entanglement used by dishonest devices. And this leads to the following: a secure protocol. So this is, now I'm going to show you a secure protocol. We are not yet in the novelty from this talk, but still in the background. So this is a protocol, a very simple, so the protocol itself is almost what you would guess as the first try if you try to design quantum position verification. So what you do is we are again in one dimensions for the moment. You have a verifier here, a prover here, and a verifier here. And verifier number 1 takes a random number x and encodes it in a random basis B, so just the stuff we sent in BB84. And verifier 2 sends this corresponding basis classically. And then at this point, they both reach the prover. The prover measures this state here in the basis B, which it now knows, and the measurement outcome, which should be x, is sent to both verifiers, and they check whether they got the answer in time. Now we know that in general this cannot be secure, I mean not against unlimited adversaries, but it was shown for the for the 1-bit case, it was already shown in the setting in the paper before. In the general setting with multi-bit strings by this paper, you can show this secure under an assumption, namely that before the protocol start, which formally means in this triangle of space-time, there are no entangled photons. Unfortunately, the 1D case is not what we are really interested in. We are interested in the 3D case, or at least in the 2D case, because we are either kind of in 3D space or on the surface of the Earth, but you're usually not walking on a line. And then you can use a very similar protocol. Instead of sending the basis from one verifier, you send two values, θ1, θ2, and the XOR of them is the basis, and you get this protocol. Unfortunately, until now, there was no proof of this protocol. There was an erroneous proof, but that doesn't count. So our result is a proof of this protocol under the same assumption in the two-dimensional case. This is sufficient if we are looking at someone who is on the plane, like on the surface of the Earth, and we want to locate him. But in the 3D case, we still leave it as an open problem. I'm a bit low on time. I don't talk about why it's tricky, except that geometry is complicated when we combine it with quantum. But instead, I tell you very quickly about a tool, the main tool we use, namely space-time circuits. So we model the prover as a quantum circuit in space-time. And then this has complicated geometrical considerations. But then we just cut the prover into different regions of space-time, analyze which region is connected to which by wires. And once we have established that, we forget all about the geometry and only look at connectivity. So let me rush through the proof of the protocol. So what we do is we take the prover. So these are all the gates that can happen in the prover, grouped by where they are in space-time. So for example, K0 is everything that is reachable by the message from the verifier 0. And this is everything that is reachable by the messages from verifier 0 and verifier 1, and so on. This way we split the circuit, we do a proof that these arrows are all the connections they are, and now we just forget how this was defined, and we just look at this circuit. And from here on, this is just reasoning about quantum circuits, geometry is out of the picture, and that's what makes things now easy. Because now we can do tricks like this circuit, instead of it just generates a state, it has no inputs. So we make many copies of this state so that for each possible value of theta we have a copy. Because of that, we can delay the input of theta because we just compute one copy of the state for every possible theta, and we put in the thetas later in the circuit. Then we group all those circuits into 3 big subcircuits, and now you can't read anything anymore, so I've cleaned it up. The situation we end up with is a quantum state is given to some circuit X. It sends 2 messages to A and B. A and B get the basis and are supposed to guess X. And this is already known by prior work to be impossible, and we have proven the security of the protocol. So let me conclude. The 2D case is solved now. We have learned the lesson. If you reason about relativistic protocols, use a formal approach like these space-time circuits. Because, as I mentioned, it was there was a wrong proof because it was going by intuition about geometry. So I suggest to always use this concept of space-time circuits, not just in position verification, but also in the so-called relativistic commitments, which have similar issues. And also, please, someone find out the 3D case, because our proof approach does not lead to a proof in the 3D case. So thank you for your attention. That's it for this talk.
Thank you. I see a question over here.
Hello, thanks for the talk. I have a question regarding the implementation of the protocol in the quantum implementation in 2D. So could you maybe go back to the slide?
I'm not sure which one you mean.
The one where you explain the basic principle regarding.
You mean this?
The one before that one.
Yeah, I'm trying with the buttons are
yes.
not in
so
this.
No, that one that was just there. Yeah,
that's 1D.
So yeah, that's 1D. Yes,
yeah.
Of course. So how does verifier 2 know the basis if they're space like separated?
Okay, the verifiers can. So this is kind of the part of the protocol where we have a race. But the verifiers can, of course, before things start, just agree on the basis secretly, or it's just pre-agreed when they met the last time or something. So we don't consider this in the protocol. But assuming you have any kind of secure communication between them, they have all the time in the world to do this before the protocol starts.
Okay, and then the outcomes?
Same thing. They get the outcomes. They won't know at this point in time whether the verification succeeded, but now they leisurely transfer the data to each other and both check, and we'll see that it wasn't. So since they time-stamped it when they received it, they can then slowly verify whether that data was correct and whether they got it in time.
Okay, thanks.
Yeah, more questions over here.
So for the 1D case, there is a lower bound to relax this assumption from no entanglement to sublinear entanglement, right? For this protocol.
What do you mean by a lower bound in this case?
There's a lower bound on the amount of entanglement that you need to. Okay, so the known attack, it needs an exponential entanglement.
Well, for that protocol, there's even a linear known attack. I mean, for this concrete protocol, it's quite easy.
But there's also a lower bound. A linear
I think that's an upper bound, but I'm not sure. I mean, it's an upper bound on how many bits you need. Okay, let's forget about words like lower bound and upper bounds. There is an attack that uses n bits of entanglement. Whether that's called
right,
upper
but
or
there's
lower, let's not care.
No, but what I meant is there's actually a lower bound that says there's no attack that uses less than a linear amount of entanglement. And my question was whether this can be easily extended to the 2D case.
Okay, which paper is saying that? I think this paper I thought was only
It's in
if there's
previous
no
one.
entanglement.
Anyway, we can discuss it later.
Just Luca, Marco.
Thank you. Yeah, my question possibly is related to the previous one. I don't know, but starting from a secure protocol in 1D, when you move to 2D, the proof miserably fail, or if you are in a 2D case that is geometrically close to a 1D case, you can sort of still extend a little bit the security of this protocol.
I haven't verified it formally, but I would be very surprised if it. I mean, you mean something like this prover is not here, but kind of like 10 centimeters off or something, and we just make a bit of tolerance, and then we know that it's not in this point, but in this area.
Yeah.
I'm pretty sure that this works, and that the proof, you just need to put a few epsilons in the proof and think 3D instead of 1D. But I think everything goes through, but I can't promise because I haven't done it. But I'm confident. And I plan to, I mean, for our result, it's in 2D. The same question applies. Is it like does it work in 3D if the verifier is, the prover is slightly out of the plane? I think yes. I haven't had the time to check that yet, but that's the plan for the full version.
Thanks.
All right, let's have a last question by Gilles.
Thanks. What is it exactly that BCF11 got wrong?
Sorry, can you say again?
You said that BCF11 got it wrong.
Yeah.
What did they get wrong, right?
The higher dimensional case. So they have a proof for the 1D case.
Sorry, so there's a proof that without entanglement they cannot cheat. Is that what you're talking about?
Exactly. There's a proof that if we assume that the malicious prover has no entanglement in a certain space-time region, so it can later have some, then the 1D protocol is secure. It also has a proof that the 3D protocol is secure under the related assumption, but that proof is wrong because, or at least I don't understand it, and Serge Fair, who was one of the authors in the discussion, also didn't understand it anymore after we discussed, so I assume this means it's wrong. So, because it was having some intuitions about geometry which seemed to not match the intuitions that the universe has.
But are we talking about the same protocol?
Yes. So we are giving a security proof here for the protocol that that was designed in the old paper in 2013.
Okay. I'll take you offline.
All right, let's thank Dominique again.